the audience, and as it so happens, the examiners are here as well, by coincidence, and so they have the opportunity to see also what you have done. So I would suggest keep it to the 20-25 minutes maximum, and if there are some kind of open questions at the end, some public questions, we have a few minutes for those, and then at 12 we will start the viva. Okay? Good.
Good morning. My name is Min Li. I studied my PhD in 2010. My PhD study is about haptic feedback of rigid tool, soft object interaction in minimally invasive surgery and medical training. This is the outline of my presentation today. So first I'll talk about the motivation and aim. And then there are two main parts of my PhD study, video feedback and multi-fingered haptic interfaces. At last, I'll summarize the achievements. First, the motivation and aim. During robot-assisted minimally invasive surgery, the surgeon will be separated from the patient. And the surgeon will sit at the console to manipulate the robot at the slave side to operate on the patient. Thus, the force feedback is not available in commercialized surgical robots. And adding force feedback requires a fundamental redesign of the whole system. So my PhD study was about rigid to soft tissue interactions with combination of different feedback methods for tumor identification. Using video feedback, multi-fingered haptic interfaces, and hybrid methods. And first, let's go to video feedback. Normally, if force feedback is provided, haptic devices are required. Those are the commercialized haptic devices. They are quite expensive. So here I propose to use cost-efficient vehicles to give stiffness feedback. So here, three modalities of the feedback I used here. First is the stiffness map, which is suitable for tiny manipulation environment, and tissue deformation visualization and cursor speed modification, which will be suitable for surgical training using tissue models. Stiffness map, I used the Phantom Omni as a 3D motion tracking machine to provide the trajectory for the fennel at the slave site to palpate on the artificial organ with a flat surface, and this force sensor at the tip of that probe to record the force information during the process. And the stiffness, real-time stiffness map is generated afterwards. In order to investigate whether the stiffness map can always be generated using different palpation speed, an experiment was conducted. 7 different palpation speeds was used here. And as shown here, it can always generate the differences among the tissue areas and other softer areas. And also, user palpation study was conducted to compare the differences among the stiffness, video stiffness feedback, force feedback, and the combination of the two methods. As shown here, the result shows that all of them don't have significant differences. So I can conclude that the video stiffness feedback has a strong potential to be used to replace force feedback. Palpation on tissue models. If a soft tissue model can be generated to represent the tissue contour information and the stiffness distribution, we can conduct the surgical training on the soft tissue, and different modalities of feedback methods can be used there. To acquire the tissue surface information, Kinect device was used here to acquire the 3D image, and then point clouds was segmented from the environment, and distributed triangles are used to reconstruct the tissue surface using OpenGL in a graphical interface. And the tissues, after we got the information about the tissue contour, this information can be registered to the robot system, and then the indentation depths can be controlled to acquire a stiffness distribution. It's shown here for different indentation depths. The stiffness distribution was acquired for this curved surface soft tissue. Apart from the stiffness map I talked before, there are some other modalities. Visualization of soft object deformation. In finite element analysis, I use the two types of hyperelastic materials, porcine kidney and silicon, to investigate the tissue deformation. And I found that using the same indenter and the indentation depths, the deformation are always the same. So a graphical deformation soft tissue model was proposed here. So if the indentation happens at the red nodule, the other vertices of the triangles will be adjusted accordingly. As shown here, when the indentation depth increases, the deformation increases as well. Another type of feedback is modification of the cursor speed. So here, if the indented avatar is approaching a tumour underneath, if we decrease the speed of it, and then increase the speed after it passed over the nodule, we can get a virtual force as it approaching the tumour. And also the two types of feedback can be combined together here to provide a more intuitive way of showing the haptic information. Also, different types of input devices I investigated. First one is the Phantom Omni. I used it as a 3D motion tracking device. And then the second one, a pressure-sensitive touchpad, which can be used to for the user to input the indentation force. But for those two types, the information of the visual feedback and the motion they input are presented at different locations. By using tablet computers, the two informations will be presented at the same location. So it is expected to have a better feedback. And my experiment confirmed that using tablet computers can generate the result as good as using manual palpation. It will be interesting to see the force feedback and the pseudo-haptic feedback combined together. So I used the Phantom Omni and graphical interface here to provide both of them. And the experiment showed that results showed that the combination method provided the result as good as manual palpation, and the time consumed significantly reduced compared to the pseudo-haptic feedback and force feedback. We've talked about the video feedback. Now I'm going to talk about multi-fingered haptic interfaces. During palpation, surgeons use more than one finger to palpate on the soft tissue to acquire more information than just a single point force feedback. And tactile feedback becomes a very hot topic, and several tactile feedback devices have been developed. However, there are so many elements it needs to be controlled, so the control system is very complex. So multi-fingered haptic feedback has been introduced here, but using those interfaces, still the control is complex, and also the surgical system needs to be modified to using them. So my aim is to develop some actuators suitable for the multi-fingered haptic feedback palpation. Two types of actuators I proposed: pneumatic actuators and granular jamming actuators. And those actuators can be easily used in the context in minimally invasive surgery and robot-assisted minimally invasive surgery to simulate the grasping palpation and non-grasping palpation. First, the pneumatic actuators. This air chamber inside the silicon structure. If there's air injected in the air chamber, the surface of the structure will be deformed and cause increase of the stress on the fingertip, which can simulate the situation happens during palpation. So I use the finite element modeling to validate the concept. So first showing here this a comparison between palpating on soft tissue without the tumor embedded and with the tumor embedded. As shown here, the stress distribution on the fingertip when there's no tumor embedded is more even than the other one. Similarly, using my actuator, when there's the actuator is inactivated, the distribution of the stress is more even than when it is activated. In order to further improve the efficiency of my actuator and the multi-fingered haptic palpation, I proposed to use the experiment. So this is the experimental setup. Pressure-sensitive touchpad is used to for the user to provide the indentation force, and there are three actuators located under the three fingers to provide force feedback. And the locations of the three fingers are showing on the graphical interface. And the experiment result confirmed that there's an improvement from the single finger palpation to the three finger palpation, and the time consumed is significantly reduced. And then another type, granular jamming actuators. So when the granular jamming actuator is not activated, this chamber is very soft. And when you palpate on it, it represents the situations happens when there's soft tissue. And when it's activated, the air is extracted from that chamber, makes it become more rigid to represent when palpating on soft tissue with tumors embedded inside. and the size of it will be reduced. In order to maintain the same height as the first one, a pneumatic chamber is added underneath to help it maintain the same height and to contact the surface, the fingertip always. And after it's deactivated, it helps the granules in the granular chamber become loose again. And I propose to use the cotton thread to be embedded on the surface of the pneumatic chamber to make the deformation of it more even. And the finite element analysis was performed to confirm that. And as shown here, the deformation is more even than when there's no cotton thread. And the indentation test was performed to show the ability of the stiffness variation of the actuator. As shown here, when the air pressure is 0.02 megapascal, there's nearly a linear relationship between the vacuum pressure and the stiffness. Also, I'd like to link the multi-finger palpation concept with the pseudo-haptic I proposed before. So I used the 3 indenter avatars to show the differences among the 3 locations. And the experiment confirmed that the consumed time significantly reduced compared to just using one indenter avatar. And then now it goes to the achievements. In summary, my research have come to those 3 main achievements. Visual feedback methods, including real-time stiffness map feedback and pseudo-haptic tissue stiffness simulation. Multi-fingered haptic interfaces, including pneumatic haptic feedback actuators and granular jamming stiffness feedback actuators, and also hybrid feedback methods. That's combined force and pseudo-haptic feedback, and multi-fingered pseudo-haptic feedback. And I have those journal publications and conference papers. That's it. Thank you.
So thank you very much for this. So thanks also for sticking to the time so nicely. Very good. If there are any burning questions from the audience, please feel free to ask. The examiners maybe want to keep their questions for a bit later. Okay, everything is clear.
Thank you.
Thank you very much again. Thank you. Good. So again, thanks for coming. And I think this is a UK first, possibly, where we have the presentation kind of in front, in a public kind of way before the viva. So thanks for being part of this experiment. I think it was very nice. Thank you. Good. So then should we maybe rearrange the tables, just turn them around so we